It's now time to address the issue of the Poynting vector as it relates to electromagnetic waves. So the Poynting vector describes the rate at which energy in the E and M fields is transported through an imaginary area, okay, a surface area. So you can kind of think of it a little bit like a flux, okay? And so the rate at which energy is transported through, that is your power, okay? So this is the power per unit area. All right, so the Poynting vector is the power per unit area, and we give this the letter S, okay? And the Poynting vector is given by the electric field crossed into the magnetic field divided by the permeability constant. Okay, so your total power is going to be your S integrated over an area. Okay. And so there's another consequence from this, okay? E cross B is the direction of the wave that's propagating. Okay, so E cross B is the direction of your propagation, and the actual calculation of E cross B represents the rate at which your energy is being transported by the fields through a given area. Okay, so if you know what area you're going to be considering, then you can get the total power that the system is delivering. Okay. So what this means is that energy is contained in the fields. Now that's nothing new. We saw the same thing with capacitors and so forth. So it shouldn't be a surprise that energy is in the fields, but as the fields are moving, they carry that energy with them. All right. But as they spread out, then the energy gets dispersed over a larger volume, and therefore the intensity of your energy goes down. But in any case, all right, so let's crank through a simple example here. So first of all, for a plane wave, right, if I have an electric field, let's actually make this along the z-axis, actually. And this is the x-axis, and my electric field looks like this. Then the y-axis would be coming out this way. Let me check that. Yes, right-handed system, your y is coming out this way. And your magnetic field, therefore, would be oscillating in the YZ plane like this. So your electric field oscillation is here, and your magnetic field oscillation is right here. Okay. And so the equations for this plane wave, if it's propagating this direction, E would be equal to whatever your amplitude is. We don't really care what the amplitude is, but so this is going to be kx minus omega t. And this is in the I direction. Oh, this is kz. Sorry about that. Z is the direction of propagation. And your B field is given by B naught sine kz minus omega t in the J direction. Okay? So what you would do to calculate the Poynting vector E cross B, and then of course we'll tack on the permeability constant. First things first, remember that I cross J is K. So the unit vector on this is going to be in the K direction. And since everything is perpendicular, we can use well, if you think of the cross product E cross B as being the magnitudes of E and the magnitudes of B times the sine of theta, the angle between them is obviously 90 degrees. Since one is in the I direction, the other is in the J direction, that's perpendicular. So this just becomes EB over mu naught when perpendicular. Okay? So that gives us E naught B naught times sine squared kz minus omega t. And remember, we have the condition that the speed of light would be omega over k. All right, so keep that in mind. And then this is going to be divided by the permeability constant. Okay, so for a plane wave, this is the kind of wave that your lasers produce. Okay, for this kind of wave, your power per unit area is given by this expression. Okay, and then you would need to integrate that over some surface area to get the total power. Okay, so for example, if you wanted to know what the power through some circular disc right? So as your electric field, or as your light rather, travels through that circular annulus, how much power is moving through it? Okay, so then you would take this expression and you would multiply it by the area A of the disk. And the reason you would do that is because your power is your Poynting vector integrated over some area. And this is since these are vectors, this has to be the dot product. And therefore, the unit vector of this circle, if it's centered on the axis of the, centered on the z-axis anyway, and it's face on, then the unit vector for your area A would be parallel to the Poynting vector. I made the perpendicular sign. It would be parallel. And therefore, the dot product just goes to integral of S times A. Okay, so if there was some sort of Z dependence, then I would need to actually integrate this explicitly, and technically this is dA. But in this particular case, okay, I don't have any Z dependence on the area of that circle, right? It would just be whatever 2 pi, pi times the square of the radius is. So in this particular case, your power would be S times A. So it would be E naught B naught sine squared of your argument divided by mu naught times 2 pi r. Okay? And you can play some interesting games. So remember that if the speed of light is also the ratio of E to B, then that means that E naught to B naught is also the speed of light. And so you can do some substitutions to write this out in just the maximum electric field amplitudes or the magnetic field amplitudes if you like. You can substitute for either E naught or B naught into this expression and it doesn't matter. Okay. But there's another interesting case. Okay. There's another really interesting case, and that is the resistor. Okay, so suppose I have a resistor of length L, and I have current I running this way, and it has some potential delta V across it. Okay, so if I have current here and I have my potential across it like this, then across the resistor, or through the resistor I should say, there will be electric field, and that electric field is pointing this direction. Okay, and if there's current, then we also have the magnetic field, and the magnetic field is making a loop, and in this case, so the loop will go like this around the resistor, and the magnetic field will be looping up around this way. And this loop will have a radius r. Okay? And so here's the question. All right? And this is a direct application of the Poynting vector and its interpretation. And that is this. Okay? If I think of a generic cylinder that is centered with this magnetic field. Okay, so this kind of harkens back to a Gaussian surface. All right. If the radius of the cylinder is also r, okay, what is So the cylinder, we're going to let the cylinder completely encompass the resistor. It'll have the same length. And I want to know the power delivered through the surface. And this is a bit of a funky way of thinking about it, okay? But without getting into the nuances of cylindrical coordinates, okay? I'm sorry, not I, but well, let's do it this way. Okay. So let's orient a coordinate system such that this is the x-axis. Z is out of the page, and Y is up. Okay. So in this coordinate system, my E field, since it's constant, can be written as delta V over L. And this is in the I direction. And this just comes straight from the fact that E is the negative integral of your potential energy no, sorry. I've got that mixed up. E is the negative derivative of your potential. But my potential is constant, and therefore delta V is just equal to EL, in other words. Sans the negative sign, but as far as your magnitudes go, which is really all we care about for that kind of justification, but that just shows that E is equal to your potential divided by your length. And we've seen that before, right? This is just a result that we're kind of rederiving. My magnetic field, on the other hand, is given by mu naught I over 2 pi r. And in cylindrical coordinates, you would get a funky unit vector here, but it's the angular unit vector because my magnetic field is cylindrical around the resistor. So without going into too much nuance, we're going to call this phi hat. So phi is the angle. Well, let's draw it this way. If I look at my magnetic field face on like this, okay, so it's looping around this way. Then if this is the x-axis, well, it can't be the x-axis. It needs to be either the y or the z-axis. So let's make this the y-axis and this is the z-axis. Then phi would be the angle that the magnetic field makes from the specified axis. Okay, so this would be in the phi hat direction. But so the result from cylindrical coordinates is that I cross phi, okay, if I do the right-hand rule, then what I see is that this Poynting vector S is going to be pointing downward into the resistor. Okay, so this equals negative, well, in this case, it's going to be constantly inward, so it would be negative r hat. It goes against the direction of your radius. But, so your energy flow is inward, okay, through this arbitrary surface. But what is its magnitude? And by the way, this inward calculation holds for everywhere on the cylinder. Anywhere I apply the right-hand rule, the rate of flow is going to be inward, okay? And so let's now do the calculation for my power, okay? So my power in this case, I don't need to do a full-blown integral because my area is very well defined. It's the surface area of that cylinder. And notice that my endpoints will not contribute, okay? So this whole S times A, endpoints will not contribute because there's no flux outward through the endpoints. Or I really should say end surfaces, the cylindrical end surfaces. Okay. So let me actually make that correction. Okay. So now we need to calculate what S is. So S is E cross B over mu naught. Okay. And E we've already got as delta V over L, I hat direction, and we're going to cross that into mu naught I over 2 pi r in the angular direction. And by the way, don't get so wrapped up in these. If you don't really want to play the cross product game with these unit vectors, and if you haven't gone through cylindrical coordinates yet, all you really need to recognize is that E and B are perpendicular everywhere, right? So that's really the bottom line. That's all you really need to do this calculation, is understand that E and B are perpendicular everywhere. And this, of course, has the 1 over mu naught out front. And so since these are perpendicular, this just becomes 1 over mu naught times their magnitudes. So this is delta V over L times mu naught I over 2 pi r. And so my mu naughts cancel out. And we have the negative r hat direction since our Poynting vector is pointing inward. But now to get the area, right? So the area of the cylinder that we're interested in is 2 pi r times L. Okay. And this is in the r hat direction. So you can think of this as negative delta V I over 2 pi r L r hat. And A is going to be dotted into that. So really we need to be precise with our vectors there. But so this is going to be negative delta VI 2 pi RL times 2 pi RL. Well, isn't this curious? To within a negative sign, we get that, well, okay, let's put the negative sign in there. The power delivered by the fields to the resistor is equal in magnitude to the power that the resistor dissipates. Remember that P is equal to IV. So what is this telling you? Okay, so there's a very interesting subtle point here. And that is that the energy delivered to the resistor actually comes from the electromagnetic fields. And then that gets dissipated as heat. So this is the power delivered by the fields to the resistor. This is the power delivered by the resistor to the environment. So this is a conservation of energy issue, but it's actually the electromagnetic fields delivering the power to the resistor. Okay? Which is very, very deep if you think about it. All right? So these fields are delivering power through these arbitrary cylindrical surfaces, if you like. But then that power is absorbed and then re-emitted by the resistor as heat. Okay. Now, this entire process happens because of the battery, but the battery itself, it is supplying the power in terms of it's generating these electric fields which then establish the magnetic fields. So by conservation of energy, the power delivered by the battery has to be the same as delivered by those fields, since it creates the fields. But it's actually the fields themselves, via the establishment of those fields by the battery, that delivers the power to the resistor, not the charge from the battery as they move through the circuit. The charges just supply the current, and then the current generates the magnetic field. The magnetic field, in conjunction with the electric field, generates the Poynting vector. The Poynting vector delivers the power to the resistor, and then the resistor dissipates that power as heat. So that is a mouthful. All right. So one last thing to note is the issue of energy density. Okay, so energy density, we use lowercase. And so U, as a function of position and time, is the energy per unit volume in a region. Right? But remember, okay, that for a capacitor, the energy density of your electric fields we found before to be 1/2 epsilon naught E squared. And then for magnetic fields, we also found the magnetic field to be 1/2 B squared over mu naught. Right? So when you have both fields present, your total energy density is the energy density of your electric field plus the energy density of your magnetic field. Let's use B. So this is 1/2 epsilon naught E squared plus B squared over 2 mu naught, right? So if I multiply this by a volume, I will get my total energy. Okay? So if I multiply this by some volume, then I will get my total amount of energy. All right? But there's something to note first, and that is this. Remember that E equals CB, but C equals 1 over the square root of epsilon naught times mu naught. And therefore, E is equal to 1 over epsilon naught mu naught square rooted times B. And therefore, E squared is equal to 1 over epsilon naught mu naught B squared. Okay? So I can use this relationship to change my second term here. So B squared is equal to epsilon naught mu naught E squared. Right? So if I plug that in, let's bring the 1 over 2 mu naught out front, and then we're going to have E naught mu naught E squared, and my mu naughts cancel, so I get 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared. So what this expression is telling you, this is the energy density of your electric field. This is your energy density of your magnetic field. But they have the same magnitude. So both fields are going to contribute equally to the total energy in a volume of space. Okay, that is the punchline. So once I have that, this equals epsilon naught times E squared. And then if I do this same substitution, if I use this same relationship, then I will also find that it is the same thing as B squared over mu naught. Okay? So whichever one you might find more convenient to use, you can, right? And therefore, you would be able to then calculate if you know what kind of volume you're using. So, for example, if I wanted to go back to the previous example and calculate the total energy in the volume of my cylinder, then I would be able to, and my volume would be equal to pi r squared L, and we already calculated our electric field. Our electric field was delta V over L. So the total amount of energy in that region would be, in this case, epsilon naught times E squared for my energy density, and then multiply that by the volume. So I would get epsilon naught times delta V over L, quantity squared, and then multiply that by my volume, pi r squared times L. So this would be pi epsilon naught, my L's cancel, pi epsilon naught r squared delta v squared. Okay, so the total amount of energy in that region would be this expression. Okay, and you could do the same thing with the magnetic field and do the same substitutions, and you would get the same answer. Okay, so the point being, to kind of recap, your Poynting vector gives you the rate at which your energy moves through boundaries, through areas, right? And it is the energy in the fields that actually, or let's put it this way, it is the fields that actually then deliver that energy to your circuit elements. Okay? And then if you know the magnitudes of your functions of your electric and magnetic fields, you can calculate the energy densities. And then if you know what volume you're going to calculate over to see how much energy total is in there, then you would just use the process of multiplying your total volume by the energy density in that region. Okay? So, I hope that helps, and we will see you in the next lecture.